Hello everyone, welcome to my presentation. I am Garvit and today I'll be discussing about my topic on weighted directed graph based automatic seizure detection using effective brain connectivity for EEG signal for the course PHN 313 signals and systems. Let's move to the topic introduction to epilepsy. Epilepsy means an epileptic seizure is a neurological disorder which is caused by some abnormal electrical activity in the brain. It affects 50 million people globally, which cause it great distress among them. Electroencephalography means EEG is a critical tool for diagnosing epilepsy by detecting brain wave patterns. However, the manual analysis of long-term EEG recordings is time-consuming as it requires long-term continuous monitoring which can take several days or weeks produce a workload on the expert. So, it highlights the need for automatic solutions to assist or help medical professionals. Typically, the traditional EEG analysis method that we use, like type domain, time frequency, and nonlinear approaches, lacks in something. Like the time domain lacks in the frequency information, and the nonlinear approaches struggle with non-stationary signals and noisy sensitivity. So, due to this issue, graph theory-based analysis or any automated analysis is a more effective alternative for for capturing the complex features of EEG signals, which basically reduces the workload on expert and it also assists with the medical professionals. So let's talk about the foundational insights and objectives in EEG-based seizure detection. So as I talked about the motivation behind focusing on this graph-based automatic seizure detection is that the manual EEG analysis is limited and it requires substantial time and effort. This automated seizure detection can reduce the workload on expert and also improve accuracy by using machine learning algorithm, the classifier, and the signal processing techniques to detect seizure and non-seizure in real time. The key concepts that we can take here about is the brain connectivity, which is nothing but the correlation between different regions of the brain that can reflect the transmission of information. It includes three types of connectivity: the structural brain connectivity, functional brain connectivity, and the effective brain connectivity. The effective brain connectivity among them is determined by sampling recorded signal at multiple time points, which provides a better understanding of brain function. The common metrics used to calculate effective brain connectivity are directed coherence, partial directed coherence, the generalized partial directed coherence, directed transfer function, and directed DTF, which is DTTF. And the basically our objective, research objective is here is to develop an automated seizure detection framework based on weighted directed model using effective brain connectivity. This system is designed to identify the seizure and non-seizure events by using the machine learning algorithm that we will use further by analyzing the connectivity between brain regions and leveraging machine learning classifiers. So let's talk about methodology overview. Our methodology for automatic seizure detection is built on structured framework that integrates signal processing, graph theory, and machine learning techniques. Each stage is crucial to accurate identification of seizure events, ensuring robustness and efficiency in the model. Our section 1 contains EEG signal preprocessing. We start by preprocessing the EEG signal using a Butterworth band pass filter with a frequency range of 0.01 to 32 Hz to remove noise. The data is then segmented into 1 second windows for localized analysis, which helps in precise seizure detection. Our section 2 contains the graph construction from EEG channels. In the next step, each EEG channel is treated as a node in the graph. The edges represent the directed flow of information between different brain regions. Our section 3 contains graph theory feature extraction. Once the graph is constructed, key theory metrics are extracted, such as characteristic path length. This measures the efficiency of information transfer across the brain. The global efficiency, this represents the overall communication within the brain network. The modularity, this captures how well the brain's network cluster during seizures. Our section 4 contains classification using machine learning. Finally, we classify the data using machine learning algorithm employing three classifiers. The support vector machine, which separates seizure and non-seizure events in high dimensional space. The random forest, a classifier that aggregates decision trees for improved accuracy. And the last one is K nearest neighbor, KNN. This classifies events based on the nearest neighbor in the feature space. So as we can see, this is the whole flow chart for our detection system. This system involves collecting brainwave signal from patients and using various techniques to detect seizure automatically. Firstly, we will go through the data collection. We begin with data collection using EEG sensor that capture electrical activity in the brain. The patient is fitted with an EEG cap and the signals are recorded for analysis. This shows how EEG helps in monitoring brain activity and is crucial for detecting abnormal patterns like seizures. Next, we will go through our signal processing. Once the data is collected, it's important to clean and filter it. The raw EEG data, as shown in the top left graph, containing various frequencies and noise. To focus on relevant frequencies, typically between 0.01 and 32, as mentioned for seizure detection. We apply signal filtering to remove unwanted noise as demonstrated in the graphs on the right. Next, we'll go to the segmentation part. The next step involves segmenting the filtered signal into small and manageable portions that can be analyzed individually. This segmentation is crucial to isolate seizure events and remove irrelevant data. Next, we will extract the features. After pre-processing, we extract key features from the signal. The image on the right represents the effective connectivity, which shows how different brain regions communicate with each other during seizures. This network representation helps us understand how seizures disrupt normal brain function. Next, we will do the classification. The extracted features are fed into classification model. The system learns to distinguish between seizure and non-seizure events, and it also learns the pattern. In the plot on the left, the red boundary separates seizure and non-seizure events. At the last, we'll move to our final outcome. By combining signal processing, feature extraction, machine learning, the system can accurately detect seizures. This is crucial for early diagnosis and intervention in the patient suffering from epilepsy. So, in this way, by emphasizing how the system can aid in improving patient care and outcomes. So this is the part in which we will do pre-processing of EEG signal. So let's move to the introduction. In this study, we employed a fourth order Butterworth bandpass filter to isolate frequencies within the range of 0.01 to 32 Hz, which is crucial for seizure diagnosis. This filter effectively discards high frequency components and psychological artifacts that could interfere with accurate seizure detection. Next, we'll move to EEG signal segmentation. Due to their long duration, these signals require segmentation before further processing. It's essential to balance segment length as long segments may not fully remove artifacts, while short segments may miss seizure events. In our approach, we used a 1 second non-overlapping window to segment the signals, optimizing both artifact removal and seizure detection accuracy. Balanced data distribution. To ensure a balanced distribution of samples across seizures, which is also called a ictal, and non-seizure, which is interictal events. We included all available samples from ictal periods. For interictal periods, we employed random subsampling, ensuring an equal number of positive seizure and negative, which is non-seizure samples. These result in 9,023 samples per category. At last, we will do normalization for our training stability. During model training, large gradients updates can negatively impact learning stability. To address this, we applied a normalization method, transforming the data into a distribution with a mean of 0 and variance of 1. This step ensures more stable and effective model training. So, at last, in summary, signal filtering, precise segmentation, and balanced data handling and normalization all play a pivotal role in enhancing the accuracy and reliability of our seizure detection system. So let's talk about the effective connectivity in epilepsy. In EEG-based data analysis, there are two key approaches, single channel and multi-channel methods. Single channel analysis focuses on the structural function relationship within individual brain regions, while multi-channel methods such as effective brain connectivity, EBC, analyze how different regions of the brain interact simultaneously. To model these complex interaction across multiple EEG channels, we use the multivariate autoregressive model (MVAR). This model captures the dynamics of brain signal recorded from multi-channel over time. Mathematically, the MVR model is expressed by this given formula. In this equation, xt is a vector representing the signal from m EEG channels at time t. AR is a P cross P matrix of coefficient that describes the linear influence of past signal on the present. And the last one, ET, is a noise vector with zero mean and covariance, this as denoted by this sigma. The coefficient matrix A and noise covariance, this sigma, can be estimated using methods like Yule-Walker equations, while the optimal order P of the model is chosen by minimizing the Akaige information criterion AIC. This model plays a crucial role in applications such as epilepsy research. It allows us to understand the connectivity and interaction between brain regions, which is particularly valuable for predicting how seizure propagates through the brain. By analyzing both the present and past instances of EEG signals, the MVR model provides a comprehensive view of brain activity over time, aiding in the study of neurological disorders. Now let's discuss two key measures of causal influence between channels, the directed transfer function or DTF and the partial directed coherence PDC. The directed transfer function quantifies the causal effect of one channel on another, normalized by the effect of all other channel. The formula for DTF is shown as following. The Hij as a function of f represents the element of transfer matrix showing the causal effect from channel J to channel I. The denominator accounts for the influence of all channels on channel I as given by the HIL as a function of S F. Now let's move to the partial directed coherence. PDC is also similar but focuses on the direct influence between channel in the frequency domain. The formula is given by this, where Aij as a function of f refers to the Fourier transform of the autoregressive model coefficients, representing the influence of channel J on channel I. This helps us understand the strength and direction of causal influence between channels based on their spectral information. Moving on, we now extend PDC with generalized partial directed coherence, which is called as GPDC, which gives a clear view of direct influence between channels. The formula is similar to PDC but takes the frequency domain into deeper consideration. The formula for GPDC is given by this. AIG as function of f once again represents the Fourier transform of the coefficients in the autoregressive model, making the direct influence clearer in the complex networks. Finally, we represent these connections in a graph. The weight matrix is used to describe the causal effects between channels, creating a visual network that helps in understanding how signals influence each other. For example, in the graph, each node represents a channel and the edges are weighted by strength of the causal relationships. Now, let's talk about the graph representation and connectivity metrics. Let's look at how we can visualize the causal relationship between different channels using graph representation and connectivity metrics. In this context, we use the MATLAB toolbox of EMVAR, multivariate autoregressive modeling, to compute DTF, PDC, and GPDC across multiple channels. This is particularly useful in understanding complex networks where multiple signals interact with each other. When calculating these measures, the frequency values are samples in the range 1 to 32 with a step size of zero point 0.5, leading to a total of 63 frequency points for each frequency f. These values gives us detailed information about the connectivity between channel over different frequency bands. By averaging the connectivity measures over these frequency points, we generate a connectivity matrix, which is denoted as W of size 23 cross 23. Each element Wij in this matrix represents the causal effect of channel J on channel I. To visualize this data, we can construct effective brain connectivity network, where each node in the graph represents a channel and each edge is weighted by the magnitude of causal influence between channels. This graph representation provides an intuitive way to analyze the connectivity structure, highlighting which channels have the most significant influence on others. This helps in identifying dominant pathways in the network. In the context of EEG-based seizure detection, the brain's connectivity is represented as a directed graph where EEG channels are vertices and the edges shows the influence between them. We use graph theory measures to extract features that helps classify seizure events. The features are given as the first one is characteristic path length. This measures the average shortest path between nodes, reflecting the efficiency of information spread in the brain. The formula for the same is given below. The second one is global efficiency. This is the inverse of characteristic path length, indicating how well information is transmitted throughout the network. The third one is transitivity. This reflects how well nodes tends to cluster based on the number of triangles formed by the connections. The fourth one is modularity. It quantifies how well the network can be divided into distinct communities or modules, important for identifying localized functional areas. In addition to the previous measures, we also have the following graph matrix that helps in analyzing EEG-based seizure detection. The first one, basically the fifth one, is assortativity coefficient, AC. This metric checks whether nodes with similar degrees are more likely to connect to each other. A positive AC indicates nodes with similar degree tends to cluster. Average clustering coefficient, which is also called as average C. It measures how likely a node's neighbor are to be connected to each other, indicating the level of local clustering in the network. We can also see all the formulas below the every measures. The third one, basically the eighth one, is node strength. This is the sum of link weights connected to a node, reflecting the overall influence of that node in the network. The last one is the graph entropy. It quantifies the complexity of the graph by measuring how well the graph structure supports efficient information distribution based on the weighted edges. We can also see the formula for total entropy also, which is nothing but the summation of every individual entropy. In evaluating the performance of the seizure detection model, we use several key metrics. The first one is accuracy. This measures the proportion of true results, both true positive and true negatives, among the total number of cases. The second one is specificity. This indicates the proportion of true negatives that are correctly identified, focusing on how well the model avoids false positives. The third one is sensitivity. This captures the proportion of true positives correctly identified, measuring how well the model detects actual seizure events. The last one is the area under curve, AUC. AUC of the ROC curve provides a single value that summarizes the performance across all thresholds, with a higher value indicating better model performance. These metrics ensure a comprehensive evaluation highlighting both the direction and avoidance of errors. The experiment results of our seizure detection framework were evaluated using the EEG signals with three different classifiers. First one is support vector machine, random forest, and k nearest neighbors. These classifiers were applied to features extracted using graph theory based methods, including direct transfer function, partial directed coherence, and generalized partial directed coherence, which estimates brain connectivity. We have two model results here, in which the first one in which we will use the patient specific model. Here each classifier performance was evaluated for individual patient using the three effective brain connectivity methods. These results will be shown in the further slides. The second one is the cross patient model. In this, the leave out patient method, like the LOO method, was used to evaluate the cross patient model. Results for each patient are sorted by decreasing accuracy, offering insights into generalization across different patients. So as shown, these are the results for patient-specific model, where we use three classifier SVM, random forest, and k-nearest neighbor, alongside graph theory-based methods DTF, PDC, and GPDC to extract features from brain connectivity networks. The best performance is given by the combination of DTF and RF, achieved the highest accuracy of 99.97%, along with the nearly perfect specificity, like 99.9%, 99%, and sensitivity of 99.95%. The KNN classifier also exhibited higher sensitivity 100% with DTF and PDC, indicating that it can effectively detect seizures, although its overall accuracy was slightly lower than RF. Now, these results demonstrate that graph based theory methods, particularly DTF, help in capturing crucial information about brain connectivity, making them effective for seizure detection. The use of these methods in combination with machine learning classifier allows us to model the complex brain dynamics more accurately. In continuation of patient-specific model results, here we see the ROC curve for the three graph theory-based methods. The first one is ROC curve for DTF, which achieves an AUC of 100. The second one is ROC curve for PDC, which achieves an AUC of 99.999. The third one is ROC curve for GPDC, which achieves an AUC of 99.99. Additionally, the feature importance plot highlights which graph features contributed the most to the model decisions. The first one is node strength, which is the most important feature showing the strength of connection each EEG channel has with others. The second one is graph entropy. It captures the complexity and disorders in the brain connectivity. The third one is characteristic path length. As we discussed, it reflects the efficiency of communication across brain regions. The fourth one is clustering coefficient, the average C. High clustering suggests a more connected neural network, typical of seizure states. The last one is modularity and assortivity. This feature assess how well the brain can be divided into modules and how similar nodes are connected. This slide illustrates the graph structure of seizure and non-seizure events by comparing the connectivity patterns in the brain during these two states. The left one is non-seizure graph. In non-seizure events, the graph shows more evenly distributed node connection with few high-degree nodes, also known as hub nodes. The degree distribution indicates that most nodes have a low degree, meaning that the brain connectivity is relatively sparse during normal condition. The second one is seizure graph. During seizure events, the graph shows a different structure with more high degree hub nodes, which create shorter paths between many nodes. The corresponding degree distribution reflects this, showing a few nodes with higher degree compared to the non seizure state. In addition to the previous analysis of graph structure and feature importance, we now delve into the degree, rank, and histogram for both seizure and non-seizure condition, which further highlights the structural change in brain connectivity. The non-seizure condition. The degree, rank, and histogram plots show that during non-seizure periods, most nodes have lower degrees, indicating fewer connections. This reflects a more distributed and less connected network, typical of normal brain states. The second one is seizure condition, which is the abnormal condition. During seizures, we observe that more nodes have high degrees, forming a highly connected network. This shift towards a small word network structure is characteristic of high activity states like seizures, where certain regions of brain, the hub nodes, become more dominant in communication. The histogram supports this, showing that more nodes are participating with higher degree during seizures. This insights from graph theory based features and degree distribution highlight how seizure states create a more interconnected network, making these features crucial for accurate seizure detection. So here are the results for the cross-patient model using the leave one patient out, the LOO method, where data from one patient were used for testing while the rest were used for training. The first one is the DTF plus RF classifier. The best performance was achieved here with an average accuracy of 98.29%, the sensitivity of 96.15%, the F1 score of 97.98, and perfect specificity at 100%. PDC, and the second one is the PDC plus RF classifier, which achieved the accuracy at 95.37% with sensitivity of 90.64% and the F1 score of 95.01% and the specificity of 100%. While still performing well, it falls slightly behind DTF in terms of both accuracy and sensitivity. The third one is GPDC plus RF classifier. This method results in an average accuracy of 95%, sensitivity of 89.81%, and the F1 score of 94.545% and specificity of 100%, showing that while GPDC is effective, it also trails behind TTF. Again, the best performance that is given by the TTF plus RF combination, which outperform the others with the highest average of accuracy of 98.29%, along with an excellent specificity of 100% at this cut. The DTF method consistently outperformed PDC and GPDC across the experiment, which also suggests that it more effectively captures the directed influence between the EEG channels, which is crucial for accurate cross-patient seizure detection. So in this slide, we will discuss about the limitation of the proposed method, which shows promising results in detecting seizures from EEG signals. The first one is the prediction delay. Although the model effectively detects seizures, but it struggles with predicting seizures in advance. The next step is to improve the model's ability to detect the period before a seizure to provide early warnings. The second one is the small dataset. The experiments were conducted on a relatively small dataset. To further validate the algorithm and enhance its clinical relevance, future work should focus on expanding the dataset and including various epilepsy syndromes to improve generalization across different patient groups. So, addressing these limitations will be the key to make this seizure detection framework more robust and more efficient and more clinically useful in the real world settings. So, at last, thank you for watching my presentation. Please feel free to reach out, and I look forward to engaging with you on this important topic. Thanks.